let me talk a little bit about the ear, okay, and sound. Now, just like uh, the eye, we're talking about detecting some wavelength, some sound wave in the air. And if that sound wave has a low frequency, then that's going to be a low pitch, like a bass versus if it's a high frequency, then you're going to perceive that as a high pitch, like high, like that. Um, if the amplitude is high, then you're going to hear that as loud. Right now, if um, your volume is set up too high, what's happening is that the amount of the amplitude being released by your headphones or your computer is too high. And so you lower that, you lower the amplitude so that the sound is a little bit quieter, is softer. Okay. Now, this is where your ear is located. Very few of us think of our ears, our inner ears, as being just slightly below your eye, but that's basically where they are. You might have heard that your nose and throat and your eyes and your ears are all kind of together. And you can see when you see it placed in the correct part of the body, how close it is to your throat, nose, and uh, eyes. Usually, when we think of our ears, we're thinking of our pinna, that outer ear, which is like a funnel that collects the sound waves and brings it inside. Now, I'm going to make this a little bit bigger um, and a little bit out of proportion so that I can kind of point out the different parts. So, as I mentioned, the pinna or your outer ear, that's like a funnel. And our ears tend to be very stable. Some people can move their ears a little bit. They have an extra muscle that's kind of left over, and they can move their ears. Uh, Other animals can do this very well. Cats and dogs can move their ears independently so that they can figure out where sounds are coming from. As I already mentioned, your pinna is your outer ear. That is the funnel that collects the um, sound waves from the environment, from the air, and pushes them into the ear canal. At the end of your ear canal, you have your eardrum or your tympanic membrane. And your eardrum is just a membrane, and when the sound waves hits it, it just kind of shakes a little. Now, attached to your eardrum are your hammer, your anvil, and your stirrups. And these guys are bones, and what they do is that they amplify the sound. They make the sound stronger. Now, you'll notice that your stirrups are attached to the oval window. And what the stirrups do is they kind of just drum against the oval window. And inside your cochlea is liquid. And that liquid then vibrates depending on how the stirrups hit against it, against the oval window. And those vibrations go from the outside and they travel inside. And depending on how strong that wave is how far it gets and with how much strength it gets to um, uh, the inside there of your cochlea, it might determine the pitch or the sound or the placement or something like that. That is then whatever information is collected is sent out of your ear via your cochleal nerve. If your cochleal nerve gets damaged, then that information can't get out. So sometimes people will have like a cochleal implant, and that will be attached to their cochleal nerve. So the implant then collects the sound information and it sends the sound information via the cochleal nerve to the brain. But if your cochlea and your cochleal nerve are um, attached correctly, then that information is sent through from the ear to the brain. Most of the time, if someone is deaf, There are a few places where that can happen. That can happen in the eardrum. If you burst your eardrum, then the sound information can't get anywhere. How do you burst that? You can burst it by sticking a Q-tip too far into your ear. If you blow your nose too hard, sometimes you can blow it out. If there's a strong sound, a loud noise, for example, let's say that you are very close to a gun being fired. Sometimes a sound that hard can burst your eardrum. In any of those cases, then that stops the information from getting to the cochlea. Now, if your cochlea is damaged, this will also affect your ability to hear. Um, and finally, if your cochleal nerve here is damaged, then that will also affect your ability to send information to your brain. Now, what you're seeing here are the hair cells. So if I go back in the cochlea, in the cochlea, the hair cells stick out. And you can see there a bunch of hair cells with their little hair sticking out. Those hair cells move depending on the vibrations in the liquid created by the stirrups. And so, depending on how those hairs move, that information is going to be sent to the brain. Now you'll notice in the pictures just below it, there is a normal, and you can see the hair cells and sort of in rows. And then you see in the picture next to it some noise damage. If you've ever been to like a concert and you stood too close to the speakers, when you left, you heard a ringing in your ears. That ringing was those hair cells screaming their last scream. When the hair cell got damaged, it started to send a signal, and your brain was like, oh, that hair cell must be hearing that pitch. After a while, your brain realizes, oh, that hair cell is damaged, and you'll never hear that pitch ever again. And the older you get, the more likely you are to just be missing a bunch of different pitches of sound that you can't hear. If you're young enough, you might have been in middle school and had an app in your phone. And if you pressed that app, you could hear a sound, like a beeping sound. And all your other classmates could hear a beeping sound, but your teacher couldn't hear it, right? Um, it basically, I don't know, at some point, some kid would be like, "What's that sound?" And the teacher would say, "I can't hear that." And everybody would find it very funny. And that's true. What was happening was really, really true. Your teacher couldn't hear it because your teacher was just older. And so your teacher had some damage. And specifically, the damage tends to be to the higher pitches. If you have a family member that's very old, maybe your grandma or grandpa, every once in a while, your grandma and grandpa will tell you that they can't hear you, that you're always mumbling. And you're pretty sure that you're not mumbling, but they're always accusing you of that. Or you'll be watching TV and they'll say, how can you hear that? I can't hear it at all. Um, that's because their damage to their hair cells is extensive. They're not deaf, they can still hear, but they can't hear low pitches, or I should say, very high pitches in reality, because there is enough damage to their hair cells so that they can't hear anything that is too high pitched or is sort of in the lower spectrum so that it sounds like a mumble to them. You have to basically scream at them for them to be able to hear. Or they could get a hearing aid, and the hearing aid just amplifies the sound in their ear, and they can hear just fine with the hearing aid. But without it, everything just sounds like a mumble. Now, you'll notice that in your inner ear, your cochlea is that a snail looking part of your inner ear. But on the other side, there are these little loop de loops, which are called the semicircular canals. And your semicircular canals are kind of like levels. Sometimes your mom or dad might be hanging a picture or doing some housework, and they use a level to see whether it's level, right? And they try to get that little bubble in the green liquid right in the middle. That means that it's perfectly level. Well, you have a set of levels inside your head, and those are your semicircular canals. And specifically, what they detect is the orientation of your head, so that if you move your head up or down, the liquid inside the semicircular canal moves, and you could see it moving there. Okay. Um, just shifting back and forth depending on how you're moving your head, side to side, up and down. Are you doing a cartwheel? Are you doing a backflip? Well, that's going to change how this liquid shifts. Inside the semicircular canals, you also have hair cells, but now these hair cells don't detect sound. They detect the liquid moving back and forth, and your brain perceives that as balance. And so sometimes you stand up too fast, and the pressure in the semicircular canal sort of messes up, and it just sort of shifts just randomly. Sorry. And so now you kind of feel like you're dizzy. Or if you're spinning around or doing a backflip, a bunch of backflips back to back, again, the signal gets sent wrong, and you perceive that as being dizzy. Now, if you're, let's say, a skater or a gymnast or a dancer, and you're used to spinning around and you're used to jumping around, well, now your brain doesn't get confused anymore because it's used to getting those signals. And so, where somebody else might get very dizzy, you don't. Now, your semicircular canals don't work independently. They use other things to make sure that you're balanced just right. So your brain gets information from the semicircular canals, but it also gets information from your eyes and from your legs and your feet. And all of these work together to keep you balanced. And if one of them goes off, then you might get motion sickness. Uh, my best friend cannot read anything in a moving car because he'll get motion sickness. What's happening there? His semicircular canals are saying, we're definitely moving. I can feel that we're moving. The head is not still. The legs are also, or your body might also be feeling, hey, we're definitely shaking around here. Um, but your eyes are saying, no, we're standing still because your eyes are focused on the page or on your screen. And it goes, your eyes are saying, no, we're definitely standing still. And your brain, when it gets all this information, it says, something's wrong. And the way you feel something is wrong is that you feel dizzy or like motion sickness. Because again, your semicircular canals are not the only part that is sending information to your brain. It's always a collective effort. Uh, there you are. You see Bart just sort of moving around. When he finishes, he's going to feel super dizzy because different parts of his body are going to be sending different pieces of information to his brain.